Welcome to Sri Learning Academy. Let's simplify pipes in operating system. We already know from earlier chapters that processes often need to communicate with each other. In the interprocess communication topic, we briefly introduced the idea that processes do not live in isolation. They frequently need to share data or send information back and forth. Pipes are one of the simplest and oldest mechanisms provided by an operating system to make this communication possible. They are especially important in Unix and Linux based systems, but the concept exists in many operating systems in one form or another. Let us start with a very natural way of thinking about a pipe. Imagine two people standing in different rooms, connected by a long tube. One person speaks into the tube, and the other hears a sound coming out on the other side. The tube itself does not understand the message, it simply carries whatever is put into it. In operating systems, a pipe works in a very similar way. One process writes data into the pipe, and another process reads data from it. The operating system manages this pipe and ensures the data flows in the correct order. A pipe is essentially a communication channel. It allows a stream of bytes to flow from one process to another. Pipes follow a very important rule. They are usually unidirectional. This means data flows in only one direction. One end is for writing and the other end is for reading. If two processes want to communicate in both directions, they generally need two pipes, one for each direction. Now, there are two main types of pipes we study in operating systems. These are anonymous pipes and named pipes. The basic idea is similar for both, but the way they are created, identified, and used is different. Let us first talk about anonymous pipes. As the name suggests, an anonymous pipe does not have a name in the file system. It is created temporarily by the operating system and usually exists only while the communicating processes are running. Anonymous pipes are most commonly used between related processes. In other words, the processes usually have a parent child relationship. A very common example comes from Unix systems. Suppose a parent process creates a child process using fork. Before or after creating the child, the parent creates a pipe. Both the parent and the child inherit access to this pipe. Now, the parent can write data into the pipe, and the child can read that data, or the other way around, depending on how the pipe ends are set up. To make this more concrete, imagine a simple command line example. You type a command like lspipe grep txt. Here, the vertical bar symbol represents a pipe. The ls command lists files in a directory. The grep command searches for lines containing a specific word. What happens internally is that the operating system creates an anonymous pipe. The output of ls is written into the pipe. Then grep reads from the pipe instead of reading from the keyboard. Neither command needs to know the details of how the other works. The pipe quietly transfers data between them. This is a very powerful idea. Each program does one simple job, and pipes allow you to combine these programs to do more complex tasks. From the operating system's point of view, it is just managing a buffer in memory and controlling read and write access. Anonymous pipes do have limitations. One major limitation is that they can only be used between processes that are related. Since the pipe has no name, unrelated processes have no way to find or access it. Once the process terminates, the pipe disappears. This is fine for short-lived communication, but not suitable for more general use. This brings us to named pipes, which are also called FIFOs. FIFO stands for first in, first out, which describes how data flows through the pipe. The first byte written is the first byte read. A named pipe is different because it has a name and exists as a special type of file in the file system. Because it has a name, unrelated processes can open it and use it for communication as long as they have the required permissions. This makes named pipes much more flexible than anonymous pipes. Think of a named pipe like a shared mailbox placed in a hallway. Any authorized person can drop messages into it, and any authorized person can pick messages up. The mailbox has a fixed location and name, so people do not need to know each other personally to communicate. For example, imagine two independent programs running on the same system. One program produces data, and the other program consumes data. They are started at different times and have no parent child relationship. A named pipe can be created in advance. The producer opens the named pipe for writing and sends data into it. The consumer opens the same named pipe for reading and receives the data. The operating system ensures proper synchronization so data is not lost or mixed up. Name pipes are often used in client-server style communication on the same machine. A server process can create a named pipe and wait for clients to connect. Clients can open the pipe, send requests, and read responses. This concept connects nicely to the client-server ideas we discussed earlier in operating system structure, where services wait for requests and respond accordingly. Another important aspect of pipes is how they handle blocking. If a process tries to read from a pipe and there is no data available, the operating system usually blocks the process. This means the process goes into a waiting state until data arrives. Similarly, if a process tries to write to a pipe that is full, it may be blocked until space becomes available. This behavior ties directly into process states and scheduling, which we studied earlier. The operating system uses these blocking points to efficiently switch the CPU to other processes. Pipes are also closely related to buffering. Internally, the operating system maintains a buffer for each pipe. When one process writes data, it goes into this buffer. When another process reads, data is taken out of the buffer. The size of this buffer is limited. This is why excessive writing without reading can cause a process to block. It is important to understand what pipes are not good at. Pipes are best suited for simple stream-based communication. They do not provide message boundaries by default. If one process writes two messages, the reading process just sees a stream of bytes. It is up to the processes to agree on how data is structured. For more complex communication patterns, mechanisms like message queues or shared memory, which we will discuss next, are often a better choice. To summarize in a very practical sense, pipes are one of the simplest IPC mechanisms. Anonymous pipes are quick, temporary, and ideal for communication between related processes, especially in command pipelines. Named pipes are more flexible, persistent, and useful when unrelated processes need to communicate using a well-known channel. Both types rely on the operating system to manage data flow, synchronization, and process blocking. As we move forward to topics like message queues and shared memory, you will notice a clear progression. Pipes focus on simplicity and streaming. Message queues add structure and prioritization. Shared memory focuses on speed. Understanding pipes first makes it much easier to appreciate why these more advanced mechanisms exist and where they fit best in an operating system. That is it for this video. See you in the next one.